So our next speaker is 5ingenelissen.
Good morning, everybody. I would like first to thank the local organizers as well as the ETPN board for this nice meeting where I had the opportunity already to meet a lot of new people, and it was very pleasant also yesterday evening, so it's great to be here. Thank you. I want to give a talk about a recent paper that we published and which concerns the behavior of nanoparticles in stem cells, which can have some implications for regenerative medicine. Nope. Okay. Well, first, the mission and vision in vitro in the health department is that we would like to contribute to a sustainable healthcare system by promoting healthy aging and personalized healthcare. So, and we do that by giving advice to policymakers in the active health promotion and primary prevention by performing biomonitoring studies. And in the second half of the slides, we also develop technological solutions for early diagnostics, disease treatment and follow-up, and also care. Okay, well, this pitch, I want to tackle the medical issue of regenerative medicine, where stem cell transplantation comes into the picture. And during the last 30 years, the stem cell transplantation has mainly been applied to the treatment of cancer, but there are different domains where also this technique is being explored and is most probably very successful. A tool to treat, like for instance, neurodegenerative diseases or myocardial ischemia and so on. But the stem cell transplantation has some issues with its efficacy, which is related to the cell survival of the transplanted cells, the homing of the cells and engraftment at the site of repair, and also their differentiation. I have no figures here because I told you yesterday I find it very difficult to find figures, but it has been told to me that less than 20% of the cells that have been transplanted survive and are able to home really to the place of repair. So there's a large window of opportunity, I would say, to improvement. And we can image those stem cells to monitor at least what is happening and to try to understand the process and to be able to tackle it. Well, current solutions on the aspect of nanomedicine, they consist of applying synthetic nanoparticles, which are mainly targeted in vitro to the stem cells. So the stem cells are loaded ex vivo, I would say, before they are transplanted. And the main mechanism behind it is that the cells take the particles up and then they get transplanted. So this is mainly for the imaging of the cells, but also sometimes signals can be given with the nanoparticles to guide and to support the cell survival and the cell functioning. Now, the current outcomes for patients is that a number of these internalized nanoparticles remain in the stem cells, so they persist there and they accumulate. So doses can be quite high, and they can also have side effects, so they can impair also cell function and differentiation. And next to that, also other cells are sometimes taking those particles up and can clear them. So there are some issues with it. Well, we propose now to have a new mechanism of loading those stem cells with nanoparticles, which would be transient. And this could either be through attaching those particles on the outer cell membrane, which would help us to circumvent the problem of uptake of particles. And in a second hypothesis, it could be that the particles are taken up, but are released again afterwards by excretion. Well, what would be the benefit for that? Well, it would mean that there's a short-term delivery of signals or imaging label, which is sufficient to influence cell behavior and to monitor the cells. And we would also like to go for active release of the nanoparticles so that they can be cleared in the system. Well, the benefit of it would be that we could give a more low dose of treatment. It could be repeated in time, so we could do a long-term follow-up. And this would substantially increase the efficacy and the safety. Well, we have some proof that this is doable because, as I told you, we have a recent paper. It's accepted but not yet published. And in this study, we exposed haematopoietic stem cells, which was primarily derived from cord blood, to polystyrene nanoparticles of 40 nanometer, carboxylated particles. And we could see that in a just 1 hour time, there was a massive intake or loading of the cells. And after that, the uptake declined again and remained at a constant level. This is a very unique observation because if you go and look in literature, you would find that if you do such experiments, then normally the load of the cells with nanoparticles would increase over time. We compared it also to dendritic cells that were derived by differentiation from these haematopoietic progenitor cells. And here at 37 degrees, you can see that we have this transient loading. But for the dendritic cells, on the right-hand side, you can see the steady increase. We could also show that this process is dependent on active, energy-dependent processes by incubating the cells at 4 degrees, so that's the gray line here. And you can see then that there's no loading if the energy-dependent processes are blocked. And the same goes for the dendritic cells. And we could also prove that the release is really an active process by first incubating the cells at 37 degrees, and then after 1 hour, when the uptake was highest, we put the cells at 4 degrees, and then you could see that the release was also blocked. So that's, I think, quite some evidence for that. And we also did some confocal microscopy to visualize this. So here you have the progenitor cells and the dendritic cells. We stained the membranes here over time. The nanoparticles are in green, and then we had nuclei. And here you can see the overlay picture where you can clearly see also the transient uptake and release again. So what's next? What needs to be done for this? Well, we need to improve our in vitro studies, so we need to determine what's the mechanism behind it. So is it exocytosis or is it just attachment to the outer membrane? We're fully doing this now, of course. We also need to establish this for different functionalizations of the nanoparticles and to see if we can also attach some targeting ligands to the particles at the same time. And of course, in the future, we should go for in vivo studies to prove that also there we can have the beneficial effect and the safety of the approach. So with that, I would like to thank you for listening, but also the people that were involved in the study. And last but not least, also the local hospitals that provided us with cord blood samples. Thank you.
Is it a fluorescent label? Or
Yes.
so how do you monitor in vivo?
Yeah, in vivo it would be more problematic, but there are some fluorogenic probes. There are some techniques like polarized microscopy that can be used for that. For large animals it works. I don't know for humans. It needs to be. But of course it's not really the purpose to keep on using the fluorescent particles. We just want to understand why, what is steering this process, and then I think we can have many variables in that.
Thank you very much.
Okay, thank you.